Thanks for coming, and welcome to our Data Odyssey. My name is Ricardo Fanjul, and I have been working for the last 2 years in the new Letgo data architecture. Letgo is a second-hand marketplace with more than 100 million of downloads and more than 400 million of listings. The amount of data that flows in our architecture is huge. For example, our users have sent between each other over 7 billion of messages since Letgo launched in 2015. 7 billion is like each person in the planet has sent a message with us. Here are some numbers of our platform. 1 billion of events processed every day, peaks of more than 50,000 events per second, more than 600 event types, 200 terabytes of data in our data lake, and the most important, we process these events in near real time, with latencies under 1 second. The road wasn't easy. We started, as many other startups, with a few users and with limited resources. Our data platform starts with a traditional BI architecture. We had a business analytics team competing for scarce resources. We began making our queries against MariaDB. Then we moved to a MariaDB slave, and as usual, the next step was a set of ETL process with the aim of copying data from MariaDB to Redshift, although the problems kept appearing. Every day, we had a growing number of users and new members joining the BI team. As a result, we started having scalability problems. Additionally, we began to have more and more complex use cases. For all this reason, the traditional BI architecture didn't meet our requirements. We needed something new. This wasn't only a data problem. All Letgo faced with similar scalability problems. So we decided to move from a monolithic architecture to an architecture based on microservices and events. So how to develop an event-driven data architecture. The first step is to understand what an event is. We have 2 kinds of events. Tracking events represent the user interaction into the app. For example, the user visit a product or the user make a search, and domain events are those events that capture the memory of something interesting for Letgo. For instance, a user has been registered or a product has been published. These are the 3 stages of our talk. We will talk from the data recollection until data exploration. The first step is ingest. In Letgo, all our teams publish domain events into SNS channels, and then we can subscribe SQS queues to these channels. Our goal was to move these events to a more data-friendly broker. In the end, we choose Kafka. For this task, we try multiple options: Apache Flume, FluentD, Kafka REST proxy, also Kinesis with Firehose, but none of these alternatives combines us. I watched a talk about Kafka Connect, and everything fitted with our idea. Kafka Connect has all the good things of Kafka, and a part of that comes with dozens of connectors. But what is a connector? Kafka Connect has 2 connector types. Source, they allow us to read events from external components and write them into Kafka, while others are sinks. They allow us to read events from Kafka and publish these events to external components. We started using an open source SQS connector, but it didn't reach the performance that we need. It only processed around 1,000 events per second, and we needed much more. So we have to develop a custom SQS connector, and it was really easy. To implement a custom connector, you only need to write a few classes, and all the difficult things are done by Kafka Connect framework with outstanding performance. This was the moment that changed everything. Now, everything that happened in Letgo is stored in Kafka in real time, so we can start thinking about how to process these events. Our journey to the start begins. The first step is how to build our data lake. We want to store all our domain events into S3 and keep them forever in order to use them later. We try 2 options. Kafka Connect, and Spark. But in order to justify our choice, we have to talk about some problems. The world is not perfect, and sometimes shit happens. Our architecture ensures that we never lose events. However, duplicating events could happen. For this reason, we decided to use Cassandra for that duplicate our events. We can write the same event into Cassandra several times, but in the end, because each domain event contains a unique identifier, Cassandra will only have one copy of the event. So we have achieved our desired duplication. After that, we only need to read events from Cassandra and write them into S3 as raw format and also in Parquet format in order to optimize our analytical queries. The next problem that we face is that sometimes events arrive late, minutes, hours, or even days later. Consequently, if we only read events from Cassandra and write them into S3, we could lose some late events. Some companies repeat this process with different intervals of time, 1 hour, 1 day, but in this way we could always lose some very late events. So we designed a solution that we call Dirty Bucket. What is Dirty Bucket? First, we read the events from Kafka and write the events into Cassandra. But in this step, for each combination between event type hour, we publish a domain event into a compact Kafka topic. Now, the Spark job only needs to read from this topic in order to know which combination of event types hours should be processed. We read the required events from Cassandra, and finally, we write the event into S3 without the possibility of losing events. There are also some problems with S3. Since S3 and HDFS are different, we face with two problems: eventual consistency and very slow renames. You might face with this error. Your job starts writing data in S3, and suddenly you receive a not found error. The reason behind this error is S3 eventual consistency. Your job writes a file to some node in S3, and after that, try to read the file again. But another file of S3 without the file receives the request. As a result, S3 returns an error. Luckily, we can use S3 guard in order to handle this problem, both in Cloudera and in Hortonworks. S3 guard works logging all the metadata changes made in S3 to external consistent storage, called metadata storage. Since metadata storage is consistent, S3i can use it to fill the missing state not yet visible in S3. Have you built a job that writes a lot of data in S3 that in the end is like frozen? It doesn't have any active tags, but is still running. What is happening? To maintain the consistency of data in case of failure, Spark writes the data to a temporal folder, and only in the last step move the data to its final location. This happens instantly in HDFS. However, in S3 is a very time-consuming operation, since moving a file in S3 means copying the file and deleting the old one. This is not convenient for big files, and even worse with many files. In order to handle this problem, we have to use the new S3i committers. In Letgo, we choose the last one, the magic committer. Now, all our events are inside Kafka in real time. We have built our data lake. Now it's time to think about how to make data processing. There are two ways to make data processing: streaming and batching. Let's start with the streaming. In Letgo, we have several apps running in streaming, and we are going to talk about two of them. The first one is real-time user segmentation. We want to classify our users in real time. For that, we build an application using AkaStream that processes user behavior events. We design it using event sourcing, and these are the steps that happens in the processing of an event. First, we have to restore the user state, reading it from the snapshot at the journal. Then we write the new event into the journal, and finally, we apply the rules, publishing a new domain event in case of a new user state has been detected. Letgo uses these events to change its behavior. For example, the notification sent by Letgo or the results showed in the feed depends on the user state. Our users also interact between each other. These are the typical questions inside a conversation among them. But for us, it was very difficult to understand what happens inside a conversation, and we want to improve our user experience. The solution for this problem was structured data. We send messages that a machine can understand. Our first idea was to improve the meeting proposal. So the user clicks on a button, select a place to meet between a list of suggested places, select the time, and finally search the proposal. And the other user receives the proposal in a nice interactive widget, accepting or rejecting the meeting. How to detect these patterns? Welcome to complex event processing, a technology that you can use in case that you need to detect patterns between events. With this technology, you can detect things like a meeting proposal followed by a meeting accepted means meeting scheduled. And we publish a domain event that represents this match. Or a meeting proposal not followed by an answer within a day. We can detect this pattern and publish a domain event. You have a pending meeting proposal. Spark doesn't have this technology, so we have to use Apache Flink for this use case. Another common use cases for thefts are fraud detection and real-time user recommendation. The next stop in our journey is batch. What seems to be the most important of our architecture is that we try to make as few batches as possible. We will see later how we do it, but for now, let's talk a very interesting batch example. This is a domain event with latitude and longitude. This is technically correct, however, it doesn't add much value. Without a context, coordinates are a lonely dot in the space. But when you provide a context, like state, city, postal code, they become something valuable. Enriching one event with this information is easy. The problems show up when you have to enrich millions of events. To handle this problem, we create geospatial indexes using GeoTools and GTS and call them from Spark SQL in order to process millions of events using only SQL. We are about to finish our journey, and now it's time to talk about data exploration. The first thing, how to query data. One ring to rule them all. But I don't want to use the language of Mordor. I want to use SQL. Let's see how to do it. Using Hive, you can read from dozens of data sources. In the image, some of the data sources used by Letgo. However, with time, Hive has become a bit obsolete for some use cases. As a result, new technologies have appeared around the Hive Metastore in order to replace Hive. The most important among them are Impala, PrestoDB, and Spark. And there is our idea of democratizing data comes in. We want to read all our data using only SQL. How we can do it? Using Spark Thrift Server, we can read from all of our data sources. We only need to create a table over some of the supported data sources, and for example, HDFS with JSON, S3 with Parquet, Cassandra, Redshift, and once done, we can query data in a unified way, making joins between data sources. One tip. What is the difference between these two create table statements? The first one uses Hive serializers and serializers, and the second one uses Spark native serializers. In our test, the second one gave us 70% speed up. As I told you before, we try to make as few batches as possible. We prefer to do it using SQL. Let's see how to do it. First, we have to create the table over some of the supported data sources, in this example, S3, and then the insertion. This statement is composed on two parts. The select, where you can make queries and joins over all your data, and the insertion. In this part, pay attention to override and partition keywords in order to append data without duplications. We run the query, Oops, we have a problem. We get 200 small files. But why 200 files? The reason is the default value of this property. And we have to add something more to our query. We have three options. Distribute by, we will get one file in this per date. Clustered by, we will get multiple files because it's an alias of the last option over all the indicated columns. And distribute by with sort by, in this case by user ID. We will get one file and the files sorted by user ID. But why could be a sorted file be important? The reason is, which is the most common Spark join? Sort, merge, join. So if we want to make a join between two tables, the first step is going to be a sort. So if we have our file sorted, the join will be much faster. We modify our query. So we want to have one file per date sorted by user ID. We run again the query, and we achieve our desired result. Now it's time to see a global vision of our architecture. On the right, some data sources. And on the left, some dashboarding tools like Superset, Bind, Tableau, and data science tools like RStudio, Jupyter, Zeppelin, all of them connected using the Spark Thrift Server and the Hive Metastore. For some people, this is the typical data science team. Adorable creatures that you want to cuddle. Yeah, but I see them as evil machines that want to destroy my cluster. Why I think in this way? Basically, data scientists are the main users of our platform. As everybody knows, sometimes users do unexpected things. Sometimes very bad things. Let's talk about data scientist scenes. Look, there are more than 3,000 small files. And as you know, small files are very bad for big data. I told you before how to fix this problem. Huge queries. Usually, we can find the same patterns inside huge queries. For example, the same condition, the same aggregation. So in order to fix this problem, we have to split these queries in smaller parts and try to pre-compute these parts hourly, daily, weekly. Too much shuffle. They not only make our queries slower, they could also fill the disks, generating instability in our cluster. The solution should be found case by case, but some tips are, we have to minimize the moved data, we have to filter out data as soon as possible. For example, adding filterings in subsellets, making aggregation in subsellets, or selecting only the required columns. For the orchestration of our platform, we choose Airflow. Using Airflow, we can see our schedule, failed or running tasks, and most important, our data scientists can develop their data pipelines in autonomous way without the help of developers. So they can explore all our data using SQL, and when they find something interesting, they can schedule the recollection of this data. As I told you before, they can create the table and then execute the insertion in the wanted frequency. For example, hourly, daily, weekly, all made using only SQL and very basic Python code. So, what do you think, Hal? He's happy now? But when we believe that we have the perfect platform, we found some problems. On one hand, we wanted to try new technologies, but in the other hand, try something new was very dangerous because a lot of features depend on our cluster, and we couldn't afford to break it. Additionally, Since our cluster was built mainly manually, starting a new cluster was a very expensive operation. So we decided to address these problems in 2 steps. The first one, moving all the data from HDFS to S3, and the second one, automating the creation of new clusters using Cloudbreak. It was a big challenge. We have to make dozens of tasks in order to complete the migration, but we did it. And we got new capabilities. Right now, we can start a new cluster in less than 20 minutes. Our clusters are dynamic, so we can add or remove instances using rules. We migrate to Hadoop 3, and the most important, we increase our experimenting capabilities. Right now, if I want to try something new, I can start a new cluster in our development environment, try in different configuration, and when I get the desired configuration, I can start a new cluster in production and redirect all the traffic. Additionally, in case of failure, we can roll back to the previous one. So, we finally arrived to our destination. And something wonderful will happen. Thanks to our new platform, we could start to try new ideas with big impact. Any sufficiently advanced technology is indistinguishable from magic. Our data scientists developed this idea within a week. Point to the product with your camera, and we make all the work for you in real time. The only way to discover the limits of the possible is to go beyond them into the impossible. This is not the end of the story. We are working in new wonderful ideas. Now is your turn. Do you want to develop the future? Do you want to join us?
So can you please explain how you dealt with the late coming events? Maybe some in-depth explanation, please.
Okay. Thank you. Each time a new event arrives, it's not important if it's the current event or very late, for example, from yesterday. We publish a domain event into a compact Kafka topic, so the Spark job that read the data from Cassandra and write the data in S3 run, for example, what time per hour. So when run, look in this topic, which combination, which hours should be processed. So read all the events from Cassandra for this hour and write them again into S3. So this is the solution.
What I know of is Cassandra is more optimized for writing and not reading. And in your architecture, you are writing everything from Kafka to Cassandra and reading a lot from Cassandra, what I can see.
Yeah, okay. We write, of course, a lot. For example, 3,000 events per second in our test. But for reading, because we are going to read, for example, event type hour, all those events are in the same partition. Well, okay, so in fact, it's very the Cassandra performance to read these events is very good. So we haven't got any problem to read events in these ways.
Okay, thank you.
Did you try AWS EMR for Hadoop? And if yes, then what benefit did you get from CloudBreak, which were not available on AWS EMR?
Can you repeat your question, please?
Did you try AWS EMR technology for Hadoop cluster? If yes, then what benefit you get from the CloudBreak?
We started using AMR, and of course, then we moved to Cloudera. We prefer, in the first time, we moved to Cloudera because in EMR, we need more control. We want to deploy more technologies not supported with EMR, and we want to parameterize more our cluster, so we need more control. This was the real fact. And the reason to move to Cloudera, for Hortonworks, is because we want a dynamic cluster. We want to start a new cluster in minutes. So it's also, Hortonworks is open source. This also was a very good reason, and mainly they are the reason. Of course, in Cloudera, we made a lot of mistakes because it was our first cluster, so we learned a lot. So in our new cluster, we put all our new knowledge. So, and of course, all the parameters are inside templates. So I can explain you later with more details.
Thank you for the presentation. How are you handle the metadata in a catalog? What is the way to handle the relationship between data, ontologies, and so on?
Okay. Yes, we use the Hive Metastore for metadata. So using the Hive Metastore, we use it from Spark. So it's the same. Using Hive, you can read from the Hive Metastore. Using Spark, you can read from the Hive Metastore. Using a Spark job, a Spark Thrift Server. So we handle the metadata with a central Hive Metastore.
So one question, how long do you stay with the data in Cassandra? Do you remove it after the Spark job has executed?
Sorry, can you repeat?
How long do you keep the data in Cassandra? Do you set a retention?
Yeah, we started keeping all the data from month without a TTL, but right now we change it to store the data in Cassandra for 3 months because we don't want to support 3 months late events. It not makes sense.
Have you ever faced OOM errors from data scientists out of memory on Jupyter notebooks or?
Yeah, of course. We faced with this error and similar ones, but what is the question?
Like, how do you handle
it depends. In fact, depends of each job. When you face with this error, maybe you need more memory, or you are using your program is not working good, because it depends. In fact, so.
So in the first slides you showed, you said like you use Kafka Connect to store data in Cassandra, and for Cassandra you use Spark to actually store them in Parquet files. Yeah. How come don't you just use Spark streaming to read data from Kafka and store them in Parquet files directly? Why do you have to use like Cassandra for this?
Yeah, maybe because Kafka Connect is really, really simple. And of course, all the clustering and all the difficult things are handled by Kafka.
But you have the complexity of maintaining a Cassandra database, which is not.
Yeah, but I think the complexity of Spark streaming to handle this amount of data is higher. So it depends. You can do the same, but we have some Spark job running in streaming. But for us, Kafka Connect is working very, very good. We never had any kind of problem with that. Spark is more difficult to maintain. It depends. You have to. It also depends on Hadoop, so it's very difficult. So Kafka Connect is very, very simple. So for this use case, with the idea of recollect data from outside, put inside Kafka or write to external component, I think is the best tool. For me, it's like a ESB in the point of view integration. So yeah, another companies use Spark for the same, or
Okay.
Flink, or there are a lot of alternatives.
You talked about late events and how how you consolidate basically events with the same unique ID in Cassandra, right?
Yeah.
And you talked about the problem of late events. Do you sometimes also have out-of-order events where you need to make sure that the record that you have in Cassandra is the most recent one for a given ID? And if yes, how do you do that?
Because we are talking about domain events, if one event has the same unique identifier, should be exactly the same. If it's different event, should have a different one. So we haven't got this problem. We write several times the same event and should be the different one.
That's all the time we have for questions. Thank you very much.
Thank you.